Black hole merger confirms Einstein and Hawking's predictions. A newly recorded collision between two black holes has delivered the strongest evidence yet that Albert Einstein's general relativity and Stephen Hawking's bold predictions about black holes were correct. What was once confined to abstract equations and theoretical arguments is now being directly confirmed through astrophysical measurements, offering an unprecedented window into the workings of the universe. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. The groundbreaking event was detected by the Laser Interferometer Gravitational-Wave Observatory, LIGO, in January 2025 and cataloged as GW250114. It confirmed that black holes are defined only by two properties, their mass and spin, and provided the most precise test to date of Hawking's area theorem, which asserts that the surface area of a black hole's event horizon can never decrease. This merger was unlike previous detections in its clarity. Scientists tracked the full sequence, two massive black holes spiraling toward each other, colliding in a titanic release of gravitational energy and settling into a single, larger black hole. The remnant weighed about 63 solar masses and rotated at a blistering pace of nearly 100 spins per second. For the first time, researchers were able to follow not just the initial inspiral and merger, but also the subtle fading vibrations of the newborn black hole, known as the ringdown. Gravitational waves, ripples in spacetime, predicted by Einstein in 1916, were first confirmed by LIGO in 2015. Back then, scientists detected the distinctive chirp produced by black holes as they merged, but the detectors were not sensitive enough to capture the faint reverberations after the merger. These post-merger signals are crucial because they encode the properties of the final black hole. Now, thanks to major improvements in instrumentation and advanced analysis methods pioneered by astrophysicists Maximiliano Ricci and Will Farr, the ringdown signal has been captured in exquisite detail. 10 milliseconds doesn't sound like much, but with today's instruments, it's enough to study the ringing of the final black hole and put our theories to the test. That brief ringing period allowed researchers to confirm a cornerstone of black hole physics. The remnant is entirely characterized by mass and spin, exactly as Roy Kerr's 1963 solution to Einstein's equations predicted. This minimalistic description, sometimes referred to as the no-hair theorem, suggests that all other information about the matter that formed the black hole is lost behind the event horizon. Equally important was the opportunity to test Hawking's area theorem. The analysis showed that the horizon of the final black hole was larger than the combined horizons of the two progenitors, meaning no area was lost in the process. This result reflects a deep connection between gravity, entropy, and the quantum behavior of matter. The results, published on September 10th in Physical Review Letters by the LIGO-Virgo-Cagra collaboration, represent a milestone in physics. They transform concepts once considered purely theoretical, Einstein's warped spacetime and Hawking's thermodynamic horizons, into experimentally verified realities. This is our clearest view yet of the true nature of black holes, Ricci explains. We're seeing that astrophysical black holes really do behave in the elegantly simple way predicted by relativity. Looking ahead, the field of gravitational wave astronomy is set for dramatic expansion. Planned next-generation observatories will be 10 times more sensitive than today's detectors, enabling the discovery of many more mergers with unmatched precision. Each new detection will serve as a natural laboratory, letting scientists explore matter, energy, and spacetime under the most extreme conditions the cosmos can offer. For so long, black hole physics was speculation on paper. Now we can actually listen to them, hear their tones, measure their properties, and confirm that our deepest theories hold true. The discoveries we are making now are just the beginning. The future of this science is going to be even more extraordinary. At roughly 4 centuries after Galileo first turned a telescope to the sky, scientists are now listening to the universe in an entirely new way. Each black hole collision adds to the cosmic symphony, affirming that our most ambitious ideas about gravity and the nature of space and time are more than just mathematics. They are reality written in